Japan is a nation defined by its islands. Stretching thousands of kilometers along the Pacific coast of Asia is an archipelago made up of more than 6,800 islands. Yet for main land masses, Honshu, Hokkaido, Kyushu, and Shikoku dominate the country's geography. Honshu, the largest, is home to major cities including Tokyo, Osaka, and Kyoto, while Hokkaido lies to the north, known for its vast natural landscapes and colder climate. For centuries, the geographical separation created by the seas and straits between these islands posed significant challenges to transportation and communication. Among these divides, the Tsugaru Strait stands out as a formidable barrier. This stretch of water separates the northern tip of Honshu from southern Hokkaido and has historically been a critical but difficult passageway. Traveling between the two islands meant relying on ferries that had to navigate not only the wide span of the strait, which measures roughly 20 kilometers at its narrowest point, but also the often harsh weather conditions that make the waters treacherous, especially during the winter months. The sea here is notorious for sudden storms, thick fog, and strong currents, frequently causing delays and dangerous crossings. Before the advent of modern engineering solutions, this meant that the flow of goods, people, and ideas between Honshu and Hokkaido was frequently interrupted. Rail connections ended abruptly on either side of the strait, forcing passengers and freight to transfer onto ferries or ships to continue their journeys. This not only extended travel times considerably, but also limited economic integration and emergency response capabilities between the regions. The idea of linking Honshu and Hokkaido beneath the seabed was first seriously considered in the early 20th century. Engineers aimed to create a direct, reliable means of transportation that would bypass the unpredictable maritime conditions entirely. Such a connection promised to integrate Hokkaido more fully into the national economy, facilitating the movement of raw materials and manufactured goods and encouraging tourism and cultural exchange. The resulting structure, known today as the Seikan Tunnel, stands as a testament to human ingenuity and determination. 85 kilometers, making it one of the longest undersea tunnels in the world. Boring through solid rock under the seabed, the tunnel passes beneath the strait at a depth of about 140 meters below sea level. This engineering marvel not only overcame the natural barrier of the Tsugaru Strait, but also addressed the limitations imposed by the region's harsh climate and geography. Constructing such an unprecedented tunnel required overcoming enormous technical challenges. The geology beneath the strait is complex, with layers of volcanic rock and shifting tectonic plates that demanded meticulous planning and constant adaptation. Water seepage and the risk of earthquakes added additional layers of difficulty. Despite these obstacles, the project progressed steadily, driven by Japan's commitment to advancing its infrastructure and enhancing domestic connectivity. The Seikan Tunnel's creation marked a pivotal moment in Japan's modern history. It transformed travel between Honshu and Hokkaido, enabling seamless rail service that greatly reduced journey times, improved safety, and ensured year-round reliability. Construction of the Seikan Tunnel began in the early 1970s, marking the start of a complex and ambitious engineering endeavor that would take much of the next 2 decades to complete. Engineers faced the enormous challenge of boring through a notoriously difficult and unstable geological environment beneath the Tsugaru Strait. The terrain included volcanic rock formations, layers of sediment, and fault lines, creating a constantly shifting and sometimes waterlogged underground landscape. To navigate these conditions, precise geological surveys and continuous monitoring were essential throughout the construction process. One of the greatest threats was water infiltration. The tunnel route lay beneath the seabed, with depths reaching approximately 140 meters below sea level at its lowest point. Engineers had to carefully control water pressure and prevent sudden flooding, which could have catastrophic consequences. The use of advanced sealed drilling machines, known as shield tunneling machines, was crucial. These machines were capable of excavating through rock and soil, while simultaneously installing concrete segment linings to support the tunnel walls and prevent collapses. The shield tunneling process involved a large cylindrical machine with a rotating cutter head at the front. This equipment allowed crews to bore forward while immediately following with reinforced concrete sections mounted to the tunnel interior. The concrete linings provided structural integrity, isolating the tunnel from surrounding water and uneven geological stresses. This method helped maintain a controlled environment in an area prone to water seepage and shifting rock. In areas where the rock was especially unstable or fractured, additional watertight sealing techniques and drainage systems were implemented. These measures directed water away from the tunnel path, relieving pressure and keeping the worksite safer. The constant presence of water required pumps operating around the clock to manage seepage. Construction teams worked from multiple starting points, tunneling inward from both the Honshu and Hokkaido sides, as well as several intermediate access shafts. This division of labor helped speed progress and allowed the use of specialized equipment best suited to each geological section. Despite intensive planning, crews had to adapt continuously, responding to unexpected soil conditions, water inflows, and seismic activity. Seismic risks posed yet another layer of challenge. Japan's location along the Pacific Ring of Fire means the region regularly experiences earthquakes. The tunnel's structural design incorporated earthquake-resistant features, such as the flexibility of the concrete linings and secure anchoring systems that could absorb ground movements without damage. Engineers also installed advanced monitoring systems to detect shifts in the tunnel structure during and after construction. The project scale was massive, 85 kilometers, making it one of the world's longest undersea tunnels and the longest rail tunnel in Japan. Construction involved tens of thousands of workers, including engineers, geologists, machine operators, and support staff. Work was often carried out in difficult conditions, including low light, limited ventilation, and confined spaces deep underground. Throughout its construction from 1971 to 1988, the project cost billions of yen and required cutting-edge technology and relentless human effort. The successful completion of the Seikan Tunnel stands as a testament to advanced civil engineering and Japan's commitment to overcoming natural barriers through innovation. The Seikan Tunnel reshaped Japan's transportation network in profound ways, creating a direct, reliable link between Honshu and Hokkaido that dramatically improved both safety and connectivity. Before the tunnel, ferries were the primary means of crossing the treacherous Tsugaru Strait, subject to cancellations and delays caused by rough seas and severe weather. With the tunnel's completion, rail travel became impervious to such disruptions, providing all-weather service throughout the year. This consistency was especially critical for freight transport and emergency logistics, ensuring that vital supplies could move steadily and quickly between the two islands without risk of interruption. The tunnel also greatly enhanced passenger safety. Ferry crossings could be hazardous in winter storms or heavy fog, but the Seikan Tunnel eliminated the need to face such dangerous conditions altogether. As a result, the tunnel not only shortened travel times, but reduced accidents and gave travelers a secure, dependable alternative. The inclusion of earthquake-resistant design elements continues to serve the tunnel well, allowing it to withstand Japan's frequent seismic activity. Maintaining the tunnel, however, is an ongoing challenge. Its location beneath the seabed means managing constant water pressure and controlling seepage require continuous monitoring and repair work. Specialized maintenance crews regularly inspect the tunnel structure, drainage systems, and mechanical components to address wear and potential damage from ground shifts. Advances in sensor technology and real-time data collection systems help detect any abnormalities early, allowing for prompt intervention. Over the decades, these maintenance efforts have proven essential to preserving the tunnel's integrity and safe operation, ensuring it remains a vital artery in Japan's transportation network. Globally, the Seikan Tunnel holds a place of distinction as one of the longest undersea tunnels ever constructed and a pioneering achievement in engineering. It demonstrated the feasibility of large-scale, deep-bore tunneling beneath an active marine environment in a seismically volatile region. The project's innovative use of shield tunneling machines, sophisticated geological surveys, and earthquake-resistant structural designs influenced subsequent infrastructure developments around the world, inspiring engineers working under similarly challenging conditions. Beyond technical accomplishment, the tunnel has had a profound impact on regional development. By linking Hokkaido more directly to Honshu's economic centers, it encouraged investment and growth across northern Japan. Industries such as agriculture, manufacturing, and tourism benefited as goods and visitors flowed more freely. The tunnel reduced regional isolation, strengthening social and cultural exchanges between the islands. It played a key role in integrating Hokkaido into national transportation and supply chains, helping balance development opportunities across the country. Ultimately, the Seikan Tunnel stands as a symbol of human perseverance and creativity in overcoming formidable natural obstacles. Its construction required vision, determination, and cutting-edge technology to tame the forces of earth and sea. Today, it serves not only as a critical piece of infrastructure, but also as a lasting testament to the possibilities that emerge when engineering meets ambition. The tunnel continues to connect people, economies, and regions, reminding us that even the most daunting physical barriers can be conquered through ingenuity and cooperation.